when we're recording. Okay, great. Oh, but we're not at the beginning. You know, you win some, you lose some. It's a Friday, and I'm just glad that I've gotten to this point. So, like I said, we're going to be talking about the second part of chapter 2. Um, and what I've tried to do with this lecture, I know that the content in the pattern recognition and binding, I know that that content was really specific in terms of all of those different theories. And so what I'm doing with this lecture is I'm zooming out just a little bit just to try to give you a larger framework within which to situate those theories. I don't think that the book does a very good job in doing that. I feel like they just jump into the nitty gritty. So this is going to be sort of a, like I said, a more zoomed out macro level view that hopefully will then help you make a little bit more sense of those specific theories in the book. Okay, so the question that was really driving the content in the second half of the textbook was, how do we go about identifying the information that comes in through our sensory systems? How do we actually make sense of what we're seeing? And so it's believed that a process called pattern recognition is what accomplishes this task for us. However, how this process of pattern recognition actually works is not completely 100% understood, but there have been a number of theories that have been developed to try to explain the process. And so the first theory, or I guess sort of category that you could put theories into, is called template matching. And so originally, cognitive researchers thought that the template matching theory, this template matching idea, was what accounted for the identification process that occurs for sensory information that we get. And so within this view, a template is a copy that resembles the stimulus. You can think of it best as like a stencil. And so then whenever we encounter an event or an object that's recognizable to us or meaningful in the information it's transmitting, we then store a template of that event or object. And then whenever we see a new stimulus, we then try to match it with one of our templates. And so there's really this sort of one-to-one ratio of, we've encountered a stimulus and now we have an image of it. Now we have a stencil of it in our memory. And so in the cases where we encounter a stimulus and the match between the stimulus and the template isn't 100% perfect, we then have a process where we set a criterion or a threshold, you know, a benchmark, say, hey, it's got to meet this before we can consider it a match. So with this in mind, like, let's say that we said it, okay, 80% of this stencil has to match up. And if it hits that 80% mark or higher, great, we call that a match. But if it doesn't, then we would have to say, well, I don't think that is a match. And so template matching, it actually works pretty well as an explanation of how computers and computerized software can identify text when the text is in like a really standardized font. So like, for example, if you've ever used text to speech, like when reading over Microsoft Word or reading text messages off of your phone, that works really well because it's this predictable, standardized text that the computer knows how to read. But there are more difficulties that arise when we move from computers to talking about complex human pattern recognition. So some of the problems with this template matching theory, again, have to do with the fact that humans, we don't behave exactly the way that computers do, right? Going back to our initial couple of lectures where we talked about, you know, some of the metaphors that have been used for how the human mind works. It's a metaphor, but it's not a perfect explanation for how the human mind works. Yes, computers and humans are similar, but it's not an exact trade-off. And so because of this, we encounter instances in the world where stimuli, they begin to look, they often look, strange. They don't match up with our templates. And so how is it that we're then able to identify this information correctly? And theoretically, this should be more difficult if we are trying to match the stimulus to a mental template. So for example, if we change the orientation so that the angle of a letter, like let's say capital R, we are still able to identify that letter as an R. If it's upside down, you can look at it and you can say, oh, that's an R. On its side, you still know that. We also have different styles of writing letters. So it's not like we only use one standardized text like computers do, but there's printing versus cursive. People write in all capitals or small letters. Differences in handwriting. Does somebody have really messy handwriting? Or even if you've ever heard of like the doctor handwriting where it's like literally just scribbles, like that's still distinguishable to some people, at least, not everyone, but it's odd. The further away from that template it is, it should be more difficult, but we still don't have any trouble really identifying it in general. Identifying like an A or an E, regardless of if it's uppercase, lowercase, cursive, whatever. And so some other examples also come to mind with respect to language. So we mispronounce words, which, the more I am giving lectures, the more I'm aware of these mispronunciations of words. We also don't speak perfectly fluently. So if you're Southern Californian, there's the stereotype that we say like a lot. And we have these other vocal interjections that we add into like, like, okay, things like that, these sort of placeholders as we continue to speak. And yet the people who are listening to us, they understand what we're saying. And also another example is in the US, we have different regional dialects. And again, our comprehension of English isn't affected. So even though words are being said in a slightly different manner than what we're used to hearing, we're still able to understand, if somebody's from Boston says park the car, you're like, park the car. Okay, got it. So it's not like we hear that and we're like, I don't know what you're saying. That's not English at all. What's happening? For the most part, we're able to still understand that. And another issue, another breakdown with the template matching theory category is that this sort of idea really only works well for these sort of isolated, complete, and other like well-formed sort of stimuli. And so there are difficulties explaining how we can recognize the whole of something from fragments or pieces. So looking at this example down here at the bottom, we can look at that and say, oh, that says word. However, a computer would not be able to make sense of that. And again, the template matching theory doesn't speak to why this is the case, why we can look at, these interruptions in these letters and we can still make sense out of it and be accurate in that too. So yet another problem with the template matching theory is it has to do with the fact that because these templates, these stencils, are assumed to be iconic, which means just, image-like, they would have to take up a lot of room and memory. And because we would have to have a great many templates as we go throughout life. We would soon have thousands upon thousands, everything, again, going back with letters, every single time you saw an A in a different font, you would then have to store a template of that, and you multiply that by however many thousands of fonts exist, and also multiply it by, well, then there's capital letter variations of that font, and etc. It's a lot. It would increase quite drastically. And so some theorists would then argue that, well, we would probably run out of memory because this is just so much information. And they would also argue that having to sift through all of these templates would take a really long time. But in response to these critiques, the cognitive theorists who put forward template matching, they did respond to some of these problems. And so they did respond to this idea of how inefficient this is, this idea where we have to literally sort through one by one these templates in our head in order to see if we can find a match or not. And so they suggested, well, we might have these sort of normalizing, standardizing routines, maybe this like more automated, streamlined assembly line sort of a thing that goes on, and that just becomes this sort of automatic routine that might do things like sort of smooth out small distortions, flip the object to its sort of upright normal position, etc., and things like that. And so they also have suggested, and research has shown us that theoretically our long-term memory capacity is infinite. You really could store an infinite number of templates plus other information in it and never run out of room. So unlike computers that are like, well, I have 4 gigs of memory and that's it, we can store things infinitely. Now, you might feel like, really, can we store things infinitely? Because I have a hard time remembering things. That has more to do with difficulty with retrieving, but at least in terms of the putting it away part, we have plenty of room where we can continue to put information away. And so we really are lifelong learners in that sense. And so there was another theory that developed out of these critiques and this breakdown of template matching theories to try to address some of the issues. And so this is called prototype theories. And so within this theory, so prototypes are thought to be of these more flexible sort of templates. They're the result of us abstracting or assembling, gathering common characteristics from various instances of an object or concept that we're encountering. And essentially a prototype is, it embodies sort of this created average of characteristics. So you might have a prototype for the concept of dog. We go, okay, dog has 4 legs, it's scruffy, it has a tail, it drools, you might have this sort of collection of characteristics to make up your prototype of dog. And so with these prototypes, like with template matching, when we encounter a new stimulus, we do another comparison process. So we do compare it to the prototypes that we have stored. And because this prototype is not a perfect copy of everything that we've ever seen, but it's more of an idealized representation of something, we're not always going to have a perfect match. And so again, like with template matching, we would need a criterion or a threshold involved in the matching process in order for us to say, oh yeah, okay, that that little, dachshund. Yes, that is a dog. Okay, got it. And so some of the evidence for prototype theory being involved in the process of human pattern recognition have been through some studies on humans. And so in these studies, people were shown a large number of stimuli that were variations on the prototype. So as an example, they're shown this triangle. Oops, that's not helpful. They were shown this triangle. Is this an isosceles triangle? I know that there are different names for triangles. Wow, high school geometry was a long time ago. Anyway, they're shown this kind of triangle, for example, and say, hey, this is the prototype of triangle. Now we're going to show you some stimuli that may or may not resemble that. And so they show them all of these different versions of triangular-like figures. And then when these participants have to look through a set of stimuli to see what they recognize, they falsely recognize the prototype as being one of the items that they had seen before. And so still this idea that, okay, yeah, this prototype does exist in our mind, and because it gets activated when we are looking through these different objects, that there's proof of that activation, right? Like that particular triangle didn't just come out of nowhere, but people said that it was a part of the stimuli. And so in addition, people seem able to form categories that are organized around these prototypes. And they can also describe the characteristics that make up the prototype. So again, going back to my dog example, like, okay, well, my prototype for dog, like I said, 4 legs, tail, when I think about it, I think my prototype for dog actually might be just golden retriever, which I don't know why, because I've never had a golden retriever in my life. Maybe it's because I want one. But anyway, so I'm able to identify this prototype and then talk about, well, what this prototype, sort of looks like in my mind. And like any good theory, criticism came up about prototype theory. And so there were some problems that apply to prototype theory that also apply to template matching theory, which makes sense because prototype theory was really just an offshoot of template matching. So one of these problems is the fact that we can still identify an object pretty easily, even when it's not in its normal upright position. And prototype theory can't really explain this. So like my dog prototype, when I think about a dog, I think of it, standing upright, all 4 legs, and I'm still able to identify a dog that's rolling around in the grass. Totally different orientation. It's down on the ground. Maybe I can't even see all of its legs fully, right? But I can still say, oh yeah, that matches with my prototype of dog. And so, well, how is that possible? And then another problem has also been that prototype theory has difficulty explaining how we are able to recognize stimuli so easily, even when we can only perceive a fragment of the entire stimulus. So again, these are some similar critiques that the template matching theory had as well. And so because of these critiques against prototype theory, researchers are kind of like, well, okay, I think we're going to have to develop another possible explanation for what's happening here. And so then a third theory called feature analysis, like I said, was developed to try to respond to the problems that were raised with template matching and prototypes. And so a number of cognitive theorists were like, well, it's a lot more efficient to have a system, sort of do this feature analysis on new information rather than having to do this sort of matching procedure back and forth that's based on templates or even prototypes. And so with the feature analysis theory, it's assumed that the distinctions that we make among the stimuli that we encounter in the world are based on sets of characteristics that are so-called distinctive features of that object. And so, for example, if the set of objects to be identified includes letters of the alphabet, then each letter can be defined by a different set of its own distinctive features that identifies it uniquely. So for an example, the capital letter A, its features might include a horizontal line in the middle, two diagonal lines that connect at the top, and an intersection of these features. And so just as of an example of this, here we have the sentence, glory may be fleeting, but obscurity is forever. And notice that it's in different fonts. Sometimes it's even just in all capitals, but we still are able to distinguish the letters because we can see that there are certain characteristics to each letter that makes it unique from the others. So like a Y is like, okay, well, it has a long diagonal and a shorter one, and they come together and it intersects not quite at the halfway of the longer diagonal. And that's really distinctive of the letter Y. We're not seeing any other letters that have that sort of set of features. And so we store these lists of features along with the label for the letter in our long-term memory. And again, here are just some more examples of feature analysis that we could do, possible characteristics of letters as we try to identify them. And you can see that there's some overlap, but each of the letters does end up being distinct, So yes, a Z does have several horizontal lines, as does an E, and those horizontal lines intersect, same with an E, but an E doesn't have a diagonal line like the Z does. And so that's the collection of features that makes the Z stand out. And so here's just another example of feature analysis, and this is for more complex stimuli such as objects. So again, we have this set of features that we can use to analyze an object. So is it straight or curved in terms of the cross section of the horizontal sort of line that we could mark across it. We also kind of have this idea of, is it bent? Is it straight? How do the sides connect with one another? And things like that. Is it rounded? Is it pointed on the end? Is it totally flat on the end? And so going back to what I was saying before the feature analysis example chart. So another assumption of feature analysis theory is that we will store these lists of features along with the label for that particular letter or object, whatever the case is, in our long-term memory. And then when we encounter a possible instance of that stimulus, the features are then gathered and compared to the feature lists that are stored in our memory. And so similar to the theories that we've talked about before, again, we would need some sort of criterion, some sort of benchmark for matching. But then the label for that feature list would be activated, and then the letter in this instance would be identified. So for example, here, you can see a variety of Bs, and similar to that list of sentences that we looked at, we know that all of the bees have certain kinds of characteristics. And so if we abstract, if we pull out those characteristics from what we're looking at here, like, okay, well, on the far left, there's a straight line. There are then these two bumps that don't come down to it, and they attach to either end of the horizontal line. We take that set of features and we go, oh, okay, that's a bee. Those are the same features as bee that I've seen before. That's what a bee is. And so some of the advantages of feature analysis is that for any given sensory domain, so whether that's visual, auditory, reading, speaking, there are a finite set of distinctive features that can be defined that can help us identify a letter or a language sound. So it's not like there are endless features to have to try to keep track of, like is the case for template theory and even for prototype theory. They're limited. Each of these sets is pretty limited. There's only maybe a couple of features, at least in the case of letters. And because these features can be coded abstractly, so as just sort of one overarching concept, rather than iconically or as like a one-to-one image representation like in template theory, this is actually more efficient and it takes up less room in our long-term memory. So it's kind of like rather than having just like random items, it's like, oh, okay, well, we can gather these items up and put them in a bag. And then, so instead of having 6 things, we just have one thing, the bag. And then we can look in the bag. And so some evidence for this theory. And so looking at animal studies, like we talked about on Wednesday, frogs appear to have retinal cells that detect specific types of features. So for instance, there are 2 important features that will determine whether a frog will recognize a stimulus as a bug and then try to catch it. And so these 2 features are, 1, the presence of a small dark spot, and then 2, the sort of bug-like zigzagging movement. And so movement that's happening in other directions, if it was like flying circularly or just maybe more in just a straight line, if it was just a dot that was registering and wasn't moving, or if a spot that it wasn't dark enough, it was really, really light. That's not going to produce any food catching responses from the frog's bug detector cells. And so only if both of these features are present will the bug be able, or will the frog be able to catch the bug. And so again, there's this idea of, okay, the frog is picking up on the various features of the stimulus, and because those features are matching up with its concept of bug, then it knows, okay, I can go ahead and I'll try to eat this fly, assuming it's a fly. Also, as you may remember, electrode recordings from cells in cats' brains show that their neuronal cells in the visual cortex, so the area that is in charge of processing vision, these cells respond only to specific features of a stimulus. And so, like we talked about, some of these cells respond to edges in a certain orientation or angle. Others will respond to movement of edges in a particular way. Still others will respond to maybe edges that are moving in one particular direction. And so it's assumed that the human visual cortex is organized in the same way in terms of looking for features. And the idea of feature analysis is also supported by human performance on cognitive tasks as well. And so in these sorts of studies, adults and children were asked to identify letters within a list. And it was found that they're able to identify letters faster when there are only a few visual features shared amongst the letters on the list. So these subjects, what they had to do was they had to decide, they were given a target letter. So let's say H, for example. And then they had to look through a list of letters and then decide whether it actually appeared in the list or not. And it was found that their decisions were faster when the letters in the list shared very few features with the target letter. And so this shows us that fewer shared features meant that the target letter was then more distinct in comparison to the other letters, because it stood out more readily to these participants. Whereas it becomes a lot more difficult when there are many shared features between a target letter and the letters on the list. So in this example here, the letter H, it does have a lot more shared features to some of these other letters. So for example, it has 2 horizontal lines on either end, or 2 vertical lines on either end. Well, so does M and N. And so it's a lot harder to pick that out. And so these confusion errors become greater when a lot of the features of the words in the list are shared with the target letter, like I said. And so also we realize that there are sorting errors that occur with higher frequency when letters share a lot of features. So when subjects were asked to sort letters that are the same into groups, they were more likely to incorrectly sort the letters that shared features, like K's and X's, in comparison to letters that don't really share features, like B's and Z's. So that is kind of the 3 overarching categories of theories that have been generated about how we go about recognizing patterns and making sense of them in our world. But the problem with all of these theories is that they are essentially bottom up, or we also call them being data driven. And so as a result of this, they have difficulty accounting for the fact that we can pretty easily figure out really ambiguous or unclear stimuli. And they also have a hard time accounting for why our processing speed is far greater than what's predicted if a full feature analysis were occurring, even though feature analysis is quicker in comparison to template and prototype matching. That is still a lot of information to dig through and try to find a match. And so therefore, a successful theory regarding pattern recognition would need to include considerations of top-down processing as well, or this sort of more conceptually driven processing. And so the assumption here is that the perceiver builds this mental understanding, this cognitive understanding of a particular stimulus or event, object, whatever it is. And so sensory information is the foundation of that understanding, right? You know, we do need to transmit the information from our senses to our brain to make sense of it. But there are also other sources of information that come into play. And this is specifically things like what we know, so our knowledge about the world, and also what we're able to infer. So this involves using higher level cognitive processing, more sophisticated cognitive processing. And so, like we talked about on Wednesday, Gestalt theories of perception hold the assumption that we do have these top-down processing abilities. We do have these innate organizing principles that then allow us to identify information based on its appearance as a whole, or more as a concept, rather than analyzing its individual pieces. And so let's look at some of the problems that come up with these bottom-up processing theories, and why we then need to think about top-down processing as well. So let's say that you present the following phrase that it's visually ambiguous. It's not entirely clear. And so this is supposed to say, the cat in the hat. But for many of us, we can easily figure out which of these more unclear letters are H's and which ones are A's. And so how does that happen? Well, prototype, template, and feature analysis theories aren't able to help us understand this. They can't explain why we're able to look at this intermixed set of clear and then unclear letters and say, oh, cat in the hat, pretty quickly. And so with respect to, speed of processing logically, so it's almost impossible for us to do a full feature analysis in the time that it takes us to identify stimuli. And so let's say that, we're estimating that each letter maybe has 4 features on average. That means that a typical reader would then have to make thousands of feature identifications each minute. And so, yes, we can read the cat in the hat really quickly, but it should take us a lot longer than that, theoretically. So it seems like a bottom-up processing approach like feature analysis doesn't best account for that. And also, like, as another example too, think about your own reading processes, right? Like in college, the amount of reading that is required really jumps up exponentially. And so you start to realize, or hopefully you've come to realize, that you're not seeing or reading every single letter in a word. Probably not. In fact, most people can read sentences quite well, even if half of the letters are missing. So does anybody want to take a stab at reading what this says down here at the bottom of the slide?
For example, it's breeze, and I don't know the rest. That's my guess.
Great. Yep.
Is it, for example, it's a breeze to read this sentence?
Yep, absolutely. So again, look at all of this information that is missing. And yet, pretty quickly, you all were able to figure out what that said. Madison, I'm sorry, did you raise your hand or did you have a question?
I was just going to read the sentence.
Oh, okay, great. But yeah. Was that what you had figured out too?
Yeah.
Okay, awesome. So see, we're able to
Professor, I have a quick question.
Yeah.
So a lot of the theories are talking about like the limits on long-term memory and the limits of how much capacity we have for like templates or prototypes and like how much we can store at one time. Has there been like research done on like what the actual like limit is, or like have we like hit that limit in research where we're like, okay, we actually can't go past this, we need to start organizing lower?
Great question. Awesome question. So in terms of our short-term memory or our working memory, we know that there are limits to that. It's actually about 7 pieces of information, plus or minus 2. We'll talk about this article that was written, I think it was in the 50s by George Miller. He called it the magical number 7, plus or minus 2. So this is this idea that we really do have sort of this span of anywhere from 5 to 9 pieces of information that we can hang on to in our working memory. But I mean, at least as far as I am aware of in the literature, there still very much is this idea that our long-term memory capacity is infinite, theoretically. Of course, this storage ability can be interrupted by things like maybe brain damage, right? Maybe you have a stroke that damages some of the tissue in your hippocampus. And so you don't actually have as much functioning storage as you used to. But the tricky thing about studying memory is there are 2 different processes, and both of them have to happen in order for us to understand whether someone remembers something or not. So there's the first process of encoding, right? You have to get that information into your long-term memory to begin with. And then there's the process of retrieval. You then have to be able to go and find that piece of information and pull it out. And so, again, in theory, we're able to put infinite amounts of pieces of information in there. You know, in general, all of us will go through life being able to encode new memories and put them into storage. The tricky part is getting them out of memory in order to verify, yes, that is actually in there. So does that make sense? I know that's a little bit more theoretical.
No, yeah, that helps. Thank you.
Okay, awesome. Yeah, it's a great question though. Yeah, it's like, it's something that, again, if we kind of use the more simplified model of computers, it's like, oh yeah, we should be able to study that. But when the rubber hits the road and you start doing studies on people, you're like, oh, this is actually more complicated. You know, studying the process of memory is actually, there's a lot that goes into it. And so, yeah, it has been hard methodologically for us to be able to see what the limits of memory are outside of just this theoretical, like, well, you technically could put an ongoing amount of information in there. Okay, so let's keep going. We're going to talk about another concept that is related to our top-down processing abilities. So one concept is called the word superiority effect. And so this concept refers to the phenomenon that people are better able to recognize letters that are presented within actual words as compared to these isolated or totally unrelated letters, just a bunch of gibberish. And they also better recognize letters in actual words in comparison to these sort of, non-word. It's pronounceable, right? In intermediate, it's pronounceable, but it's still a non-word. And so when we compare blankety blank, how quickly we're able to find E in comparison to intermediate, and also this one, the gibberish one, our eye goes a lot faster. We're a lot quicker to find the E, and that's because our mind is used to words. And so because of that, the word is like in its name is what's superior. That's going to be driving us, because our experience with that word then means that our brain has this predictableness to it of like, oh, yep, okay, blankety blank, okay, yeah. Even if you've never seen the word blankety blank before, you've seen blanket, right? Your mind is familiar with that. And so you're drawing on your previous experience with words to top-down process rather than having to go through, okay, that's a B, that's an L, that's an A, this more tedious laborious process. But with, totally unrelated letters, you might have to go through a little bit more of a B-L-A-N-I-O. Oh, there's the E. And so we also see this in what's called a configural superiority effect. And so this is essentially the idea that objects that are presented in some sort of arrangement are easier to identify than those things that are presented in isolation. And so if you were to present a participant with these 4 diagonal lines and then ask them which one's different, because these are configured closer to each other, again, going back to our Gestalt psychology, we're grouping them sort of more based on proximity to each other, right? It's a lot easier to go, oh, okay, yeah, it's the one, towards the bottom on the right, whatever, versus if they were more spread apart and they weren't really organized in kind of this sense of proximity, it would take you a little bit longer. And so our perceptions of size and also shape constancy show that there are higher level constructive processes that are at work. So, for example, as you move away from a door, so the retinal image decreases, but in your mind, the door, it's not like the door is shrinking in size. You're still able to, constantly maintain that sense of that shape in 3-dimensionality. And this is also true with color constancy as well. So, so despite changes in lighting conditions, for the most part, we're able to maintain our perception of color of familiar objects. So, if I go out to my car, I drive a red car. If I go out to my car at dusk, it doesn't appear as bright red as it does, in the middle of the afternoon, but it still does have a reddish appearance, and the color still stays constant. And I know that that color is constant. I know that it's not like, oh, well, my car turned to like a darker maroon color. Like, that's so weird. It's like, no, I know it's still red. It's just lower light conditions. Okay, so I'm going to show some videos that are also going to demonstrate some of these, how this top-down processing works in our brain.
The monkey business illusion.
Just real quick, can everyone hear this? Are you able to hear that beginning?
Yes.
Cool, great, thank you. I did it. I'm figuring out the technology, yay!
Count how many times the players wearing white pass the ball. The correct answer is 16 passes. Did you spot the gorilla? For people who haven't seen or heard about a video like this before, about half miss the gorilla. If you knew about the gorilla, you probably saw it, but did you notice the curtain changing color or the player on the black team leaving the game? Let's rewind and watch it again. Here comes the gorilla, and there goes a player, and the curtain is changing from red to gold. When you're looking for a gorilla, you often miss other unexpected events. And that's the monkey business illusion. Learn more about this illusion.
Okay, and so now we're going to watch another video, and it's actually going to involve a short interview with Daniel Simons, who's actually the researcher of that monkey business study. It was a really famous study in cognitive psychology. And like he said, in their study, about 46% of the participants did not even recognize that there was a gorilla that was just walking through.
You are about to take part in a quick experiment. Take a look at this.
Also, the beginning of this is a little bit cheesy, so I apologize.
Okay, now, did you happen to notice anything odd? Watch again. See any changes? Don't worry if you didn't see that it's two different men. It means your brain is doing exactly what it should be. It's focusing on the meaning of the scene rather than on the irrelevant details. Imagine how much energy and brain mass it would take for us to remember every single person, place, or thing we encountered. The things that matter, a conversation with a coworker, your child's first step, would be drowned by a deluge of information. So when there are minor changes to the world around us, we often don't pick up on them. There are two similar phenomena at work.
Inattentional blindness is the failure to notice something that's fully obvious right there in front of you when your attention is engaged on something or someone else. Change blindness is a failure to notice a difference between what's there right now and what was there a moment ago.
Scientists such as Daniel Simons from the University of Illinois have spent years devising experiments testing just how perceptive and unperceptive humans actually are.
So we feel like we're aware of everything, that we're taking in all of the details, and that if something important happens, we'll automatically notice it. It'll capture our attention. The reality is that we often don't notice unexpected things because we're aware of far less of our world than we think we are.
So how much or how little are we actually aware of? We decided to recreate one of Simon's most famous experiments to see for ourselves. Here's the setup.
Our senior series producer, Vin, poses as a lost pedestrian and asks a passerby for directions.
Excuse me, I'm looking for the skyline.
Then, we break the two up, walking through them holding a large sheet of wood. Now watch as I replace Vin. You might think people would notice the switch, but almost half the time, they didn't. Of course, that means more than half the time they did. We only tried the experiment 9 times, and by no means was it good science. But we were surprised 4 people didn't notice the switch. In Simon's original experiment, 7 out of 15 people didn't either. So what determines whether or not you can figure out the switch?
When you look at another person, you encode what's relevant for what you're doing right then, in that case, giving directions, and you don't pay attention to the details that are irrelevant, say what color their shirt is or exactly how tall they are. As long as you are able to make sense of the meaning of the scene and roughly the main categories of that person, say their height, their age, what race they are, what sex they are, as long as those important things don't change, the meaning of the scene really hasn't changed and you're not going to notice that anything's different.
Scientists have documented inattentional and change blindness since the 1970s, and while they allow you to focus your attention, this failure to see every detail can prove costly. Drivers often cause accidents because they overlook quick changes to their environments, such as pedestrians or cyclists. Faulty memories can wreak havoc during eyewitness testimony.
The goal of vision isn't to build a photograph or a complete model of the world in your mind. The goal of vision is to make sense of the meaning of the world around you. Being aware of our limitations can help us adapt and compensate for them, allowing us to do things that prevent the really negative consequences that can happen due to failures of awareness.
For example, Simons thinks that people might be willing to put away their cell phone when driving if they just understood the limits to their attention. Juries might realize that eyewitness testimony is far from ideal.
A little old.
And the next time you and a friend are fighting about the details of a past event, it's likely you're both wrong. Now that's something to remember.
So we have talked a lot about these two, broad groups of theories. So one of these groups, and that includes the template matching, prototype, and feature analysis, emphasizes this idea of bottom-up processing, really constructing something out of the details. And the other involves top-down processing. And there's evidence for both types. And so this suggests that elements of both are probably correct. If we put these on a continuum, with top-down and bottom-up on either side, an extreme version that leaned more towards top-down processing, it's not going to be correct. It's not going to accurately explain our perception because it would really drastically underestimate the role of sensory data and how we process information about the world. And if we were to rely just on top-down processing, we would be pretty vulnerable to making a lot of errors. We would be then relying purely on our expectations and our past experiences rather than responding to what's in front of us in the here and now. And on the opposite side of things, if we took a more extreme view of bottom-up processing, this is also going to be unlikely because this doesn't allow for the influence of our past experiences and our expectancies to influence how we're processing sensory information. What's the use of our knowledge that we have gained about the world if we can't use it to help us interpret the world in our present situation? So it could be the case that the encoding of stimuli starts the process of pattern recognition by a more bottom-up process, such as template matching or feature analysis. And then as this process continues, our expectations are then activated by these top-down processing processes so that there are certain patterns that we then look for in likely places. And there is some neurological research to suggest that this is the case. And so, for example, like we talked about with visual pathways, the very first stage of the visual pathway represents only what is the retinal image of the object. And then very quickly, the representation is then influenced by our interests, our past experiences, our attentional focus, and things like that. So then what happens when our perception goes wrong? And so there's a deficit that can be caused by damage to the brain, whether that's through, an accident or surgical lesions, even by hypoxia, which is oxygen deprivation in certain areas of the brain. And so when someone is having a perceptual difficulty of some sort, it's called an agnosia. And agnosias involve severe difficulties in someone's ability to perceive sensory information, so to make sense of what's coming in, despite normally functioning sensory systems. So it's not that there's anything structurally or physiologically wrong with their eyes or their sense of taste or their tactile abilities, their sense of touch, anything like that. The issue isn't at that level, it's within the brain itself, the meaning making part of it. And so there's a neuroscientist, Luria, in 1973, he wrote about a case report of a patient who, upon seeing a pair of glasses on his desk, first identified, well, there's this circle of one of the lenses, and then he identified, oh, there's another circle over here, and then he saw this crossbar between the two circles. And at that point, he then guessed that he was looking at a bicycle. So he was able to see the details of this object, right? But he wasn't able to zoom out and have an understanding of it as a whole. He wasn't able to make sense out of its small parts, or at least not accurate sense, right? He was like, that's a bike. And it clearly wasn't. And so one of the most dramatic agnosias is called astereognosis. And this is the inability to recognize an object through touch. And this is often accompanied by left-sided paralysis. This is because the part of the brain that is damaged in this instant is on the right side. So again, remembering contralateral control, the right side of the brain is damaged, and that's therefore resulting in left-sided paralysis. And so the right parietal, so up in the upper lobe at the top of the brain, visual cortex is what's damaged in this case. And so in people who have this difficulty, they ignore the left side of their bodies, the left visual field of the world. Sometimes some of them aren't even able to recognize their own arm, their own left arm. So if you point it out to them, they might be like, ew, gross. Like whose arm is in this hospital bed next to me? And then this deficit also extends to the external world as well. So as an example, this is a clock drawing, a drawing of a clock that somebody with a left-sided visual agnosia drew. And as you can see, they totally neglected the left side of the clock. And they put everything on the right side because that's all that they were able to make sense of. And so just real quick, there are other agnosias, depth, motion, color, auditory, those are all pretty much self-explanatory. Another really interesting agnosia is called prosopagnosia. So this is the inability to recognize particular faces. And so in these situations, people have damage that's bilateral, so on both sides of the brain. And it's the damage is on both sides of the occipital, so the right and left occipital, which again is involved in vision. And then it extends forward into the temporal lobe as well. And so this has suggested to us, and we have actually found evidence for a particular cortical region that's involved for facial recognition. And so patients with prosopagnosia, they can identify a face as a face. You show a face to them and they don't say it's a potato or a balloon. They know it's a face. They're able to identify parts, so they can point and say, those are two eyes, a mouth, ears, nose, etc. And they can even identify specific emotions of like, oh, okay, well that's a smile, so that must mean that that person's happy. But they aren't able to identify a particular face as belonging to a specific person. So they're not able to recognize loved ones, friends, or even themselves when they look in the mirror. They can say, oh, that's a face, but they don't recognize that that face is me. And so the evidence here is that it's not the knowledge of the person's identity that's been lost. It's not that they've forgotten who they are. It's just they are no longer able to make the connection between the visual stimulus of the face, either in the mirror of themselves or in a loved one, and then the knowledge about who that person is. And in order to recognize people, patients who have prosopagnosia, they have to come up with these sort of compensatory strategies. So they have to use non-visual cues like, smell somebody's perfume or shampoo or something like that. Maybe the quality of what their voice sounds like. They might even have to look at visual cues that aren't associated with the face necessarily. So somebody's hair color, maybe the shape of their teeth, maybe the way that they tend to walk, or their sort of characteristic hand gestures. And I know that we are a little bit over time, so I'm going to go ahead and stop, but I just want to check in and see, does anybody have any questions?